My name is Ludwig Sidenmark. I'm a PhD student at Lancaster University, and I'll present our research project BimodalGaze, which received an honorable mention award at last year's ETRA. And this project was done in collaboration with Diako Mardanbegi, Argenis, Ramirez, Clarke, and Hans Gellersen. BimodalGaze is a novel gaze pointing technique for seamless head-based refinement of a gaze cursor. And the technique leverages insights into eye and head coordination to classify and identify the difference between natural head movement and explicit gestural head movement. And we utilize this for seamless head-based refinement of a gaze cursor, allowing users to quickly shift their gaze to targets with naturally combined eye and head movement and to refine the cursor position with gestural head movement. And I'll present the design of the technique and results for how it supports this type of interaction. Gaze is natural and fast with pointing, but poor for fine-grained cursor control and selection. Alignment over a target is not precise, and combined with eye tracking calibration and measurement limitations, induces uncertainty into gaze estimation. A variety of work has tackled this issue by using a second modality to refine the gaze position. The head is interesting for this purpose as it is stable and precise while still allowing hands-free pointing. Head correction of gaze has been demonstrated on, for example, desktop displays where gaze shifts are performed by the eyes alone, allowing head movement to be treated as separate input for cursor refinement. However, only small gaze shifts are performed solely with the eyes. Larger gaze shifts naturally feature head movement to comfortably reach targets. It is therefore not straightforward to use head movement for gaze correction, in particular when gaze is considered for pointing across larger fields of view, such as in virtual or augmented reality. To avoid usability issues caused by refinement being triggered unexpectedly, there is a need to be able to distinguish between natural head movements performed during gaze shifts and gestural head movements that are independent from gaze. Previous work on pinpointing has made this distinction by requiring the user to manually toggle between pointing and refinement. In our work, we aim to automate this process. BimodalGaze uses gaze as the primary modality for quick and effortless pointing. When gaze is not accurate enough for selection, the technique allows automatic switching to head refinement when users perform deliberate head movements. BimodalGaze leverages eye-head coordination insights to decide if a head movement is gestural for refinement or a natural movement during a gaze shift that should be ignored. In BimodalGaze, all head movements above a simple velocity threshold are processed and classified as either natural or gestural. And we have shown in previous VR work how natural head movements are used to further the range of the eyes or to move the eyes into a comfortable position. And based on this insight, we define two criteria to define natural from gestural head movements. First, a natural head movement starts within a certain time period after an eye movement. And second, a natural head movement will move in a similar direction to the prior eye movement. The first criterion relates to the timing of head movements. Natural head movements occur at the same time or shortly after the eye movement. As such, we assume that a head movement is natural if the head moves within a certain time period after the eyes move. The second criterion relates to the movement's trajectories. As natural head movements are used to comfortably increase the eye's reach, it is reasonable to believe that a natural head movement will move in a similar direction as the eyes. A head movement is then defined as natural if the angular difference between the trajectory of the eyes and head are within a certain range. If these criteria are not true, we assume the head movement to be gestural and the technique switches to head refinement. The technique will switch back to gaze mode during deliberate gaze movements, which we define as any gaze movement over a velocity threshold. Alternatively, the system will switch back to gaze mode if the distance between the gaze and pointer position is greater than a threshold. And this is to prevent the cursor becoming too detached from the gaze due to a misclassification of a natural head movement detected as gestural, or due to eye movements which are not detected as deliberate gaze movements. We conducted a VR user study to evaluate how bimodal gaze performance is affected by target distance and accuracy error. We also assessed the effectiveness of the automatic switching between modes by comparing it with the eye and head pinpointing technique, where the switch is manually triggered via a button hold down. The selection of thresholds for bimodal gaze has a large impact on its behavior and requires careful consideration. The gaze and head velocity thresholds were set to relatively high values to avoid unintentional switches caused by minor movements. The timing and trajectory thresholds were based on our prior work on eye-head coordination in VR. Head movements generally start moving 150 milliseconds after the eyes, and we also found that for 90% of all gaze shifts with accompanying head movement, the eye and head trajectory were within 20 degrees of each other. Finally, we set the fail-safe threshold to a moderately low value so that the pointer position can be freely adjusted while not being able to move too far out in the periphery. So the headline results from the study are: users are able to rely on gaze when gaze only is enough for accurate selection. This makes bimodal gaze different from pinpointing, as head refinement is optional rather than enforced. All participants successfully completed all selection tasks, and when gaze was too inaccurate or initial selections were erroneous, users had no problem correcting their input. Bimodal gaze enables selection of targets that cannot be acquired with gaze alone, and participants are able to successfully select all targets irrespective of scale of eye tracking error. The results show that the switching between gaze and head modes can be automatic using the underlying knowledge of the way in which our head movement support gaze. The advantage is that our technique does not require explicit input for mode switching, resulting in a more seamless transition. And this also allows bimodal gaze to be combined with confirmation techniques such as dwelling to make the whole selection hands-free. And looking even further ahead, the distinction of natural and gestural head movements makes it possible to attach different behaviors to objects that take gestural head movements as input while avoiding unwanted behaviors caused by natural head movements. For example, gestural head movements could be used to manipulate gaze on objects. However, the study also pointed towards some performance limitations. In comparison to pinpointing, bimodal gaze had a higher error rate and was on average slightly slower for selection by around 140 milliseconds. And this was mainly due to two factors. First, a common situation that led to errors in gaze mode was the natural overshooting or undershooting of the primary saccade. This, combined with a high accuracy error, caused the pointer to appear on the target when the participant's gaze was not. The participant would then perform a selection. However, when the button press was registered, the participant's gaze had moved onto the target, which in turn moved the pointer outside the target. And clearer pointer feedback or target acquisition techniques could improve this aspect. Second, the high head velocity threshold caused difficulties in identifying small head movements needed for minor refinements. As such, users would either rely on gaze mode, causing incorrect selections, or perform exaggerated head movements that would overshoot the target. To improve performance, we recommend using more sophisticated techniques and models, for example via machine learning, to detect head movements. Please refer to the paper for full study details. So in conclusion, leveraging eye-head coordination insights allow automatic refinement of gaze pointing for accurate selection, which is significant as it removes the need for any manual or other explicit input, thus making the process more seamless. The notion of classifying natural and gestural head movements extends beyond refinement of a pointer, opening up new opportunities for mapping gestural head movement without affecting the head's natural ability to support gaze. And that is all for my talk. Thank you for listening.